Let's begin with the definition of differentiation. Differentiation is the process of finding the rate of change of a quantity with respect to another. It also represents the gradient or slope of a curve at a point. Let's go through the types of differentiation techniques. There are 6 techniques of differentiation. The first one is power rule. This rule is applied by bringing the exponent down to the front as a multiplier, then subtracting 1 from the original exponent. dy dx x to the power of n equals to nx to the power of n minus 1. Next is product rule. This rule is used to find the derivative when two distinct functions are multiplied together, where dy dx equals to uv prime plus vu prime. Next is quotient rule. This rule is used to find the derivative of a function that is the ratio of two distinct functions. dy dx equals to vu prime minus uv prime divided by v square. Number 4 is chain rule. This rule is used to find the derivative of composite functions by taking the derivative of the outer function while keeping the inner part the same, then multiplying the result by the derivative of the inner function. Number 5 is implicit differentiation. This technique is used when y isn't isolated on one side, where x and y are mixed together. Last one is trigonometric differentiation. This technique is used to find the rate of change or gradient of periodic functions like sine, cosine, and tangent.
My name is Elia and I'm going to explain on how to find the function for both question 2a and 2b. For question 2a, we are given y equal to 10, 1 negative x times natural log of x squared. Therefore, we need to find the derivative of it. Since there are two functions multiplied together, I use the product rule formula, which is dy over dx equal to u prime times v plus u times v prime. I let u equal to 10, 1 negative x and u equal to natural log of x squared. First, I differentiate u and I use the chain rule with z equal to 1 negative x, so it became du over dx equal to sec to the power of 2 in parenthesis sec multiplied with dz over dx. The derivative of 1 negative x is 1, so u prime equal to sec to the power of 2, 1 negative x also multiplied with negative x. Therefore, u prime negative sec to the power of 2 in parenthesis 1 negative x. Next is to differentiate v. Our v is natural log of x squared. Again, I use the chain rule and I let z equal to x to the power of 2. Became dv over dx equal to 1 over z multiplied with dz over dx. The derivative of x to the power of 2 is 2x. It became dv over dx equal to 1 to the power of 2 multiplied with 2x. Therefore, our v prime is 2x. Next, we have to apply our information into the product rule. So I substitute u prime and v prime into the product rule and I got dy over dx negative sec to the power of 2, and in parentheses we have 1 negative x cos bracket times natural log of x squared in parentheses x to the power of 2 plus 10 in parentheses 1 negative x multiplied with 2 over x. And the final answer is dy over dx equal to negative sec to the power of 2 in parentheses 1 negative x multiplied with natural log x squared plus 210 in parentheses 1 negative x over x. Now, for part 2b, we need to find the derivative of y equal to 2x to the power of 2 plus 3 over sine x. Since the function is in fraction, I use the quotient rule, which is dy over dx equal to v times u prime plus u times v prime over v to the power of x. To find our u and v prime, we must let u equal to 2x to the power of 2 and v equal to sine x. To begin with, we need to differentiate both u and v. We need to differentiate the numerator and denominator separately. And our numerator is u and denominator is v. Since the derivative of 2x to the power of 2 is 4x and the derivative of 3 is 0, for u, it will become u prime equal to 4x. As for v, the derivative of sine x is cosine x. And that is our v prime. Next, I substitute our u, v, u prime and v prime into the quotient rule and I got sine x times 4x subtract to 2x to the power of 2 plus 3 and multiply with cos x over sine x to the power of 2. After simplifying, I got dy over dx equal to 4x sine x subtract to 2x to the power of 2 plus 3 multiplied with cos x over sine to the power of 2x. And that is the final answer for 2b.
Let's move on to the question number 3. I will explain how to solve this implicit differentiate question. We are given natural log of y plus cosine square of open bracket x cubed plus e to the power of 2y close bracket equals 3xy. Our objective is to find dy over dx. Step 1. Differentiate both sides. First, we differentiate natural log of y. Using the chain rule, the derivative of natural log y is 1 over y times dy over dx. Next, let u equal x cubed plus e to the power of 2y. The derivative of cosine square u is negative sine 2u times du over dx. the derivative of x cubed is 3x squared, while the derivative of e to the power of 2y is 2e to the power of 2y times dy over dx. Therefore, du over dx equals 3x squared plus 2e to the power of 2y times dy over dx. For the right hand side, we use product rule. The derivative of 3xy is 3y plus 3x dy over dx. Step 2. Substitute the derivatives. After finding the derivative of each term, we substitute all of them back into the differentiate equation. At this stage, the equation contains several terms involving dy over dx. Step 3. Expand the equation. Next, we expand the equation by multiplying the sign expression with every term inside the bracket. This removes the bracket and makes the equation easier to simplify. Step 4. Collect the dy over dx term, then we move all the term containing dy over dx to the left hand side of the equation. All remaining terms are moved to the right hand side. After that, we factor out dy over dx from the left hand side. Step 5. Solve for dy over dx. Finally, we divide to both sides of the equation by the coefficient of dy over dx. This isolates dy over dx and gives us the final derivative. The final answer is dy over dx equal to the quantity 3y plus 3x squared multiplied by sine of 2 times the quantity x cubed plus e raised to the power of 2y divided by the quantity 1 over y minus 2 e raised to the power of 2y multiplied by the sine of 2 times the quantity x cubed plus e raised to the power of 2y minus 3x.
Next, I will be presenting the solution for question number 4, which asks us to use linear approximation to estimate the value of 8.02 square minus 1 over the cube root of 8.02. Correct to 2 decimal places. Alright, let's break down the solution into 3 simple steps. For the step 1, define the function. First, we need to create a function based on the expression. We let fs equal x squared minus 1 over the cube root of x. To make differentiating easier, we write it in index form as fs equals x squared minus x to the power of negative 1 over 3. Okay, next, we find its derivative f prime x. By applying the power rule, we get 2x plus 1 over 3x to the power of negative 4 over 3. We also identify our delta x, which is the change in value. 8.02 minus 8 equals to 0.02. Alright, let's move on to the step number 2. Choose the references value. As shown in the purple box, our given value x is 8.02, which is a nearby value s0 equal to 8 because it is easy to calculate both the square and the cube root of 8. Okay, for the last step, step number 3. Apply the linear approximation formula. Now we substitute our value into the formula. F of S0 plus delta S is approximately equals to F of S0 plus F prime of S0 times delta S. This gives us F of 8 plus F prime of 8 times 0.02. By substitute 8 into our function and its derivative, we get 8 squared minus 8 to the power of negative 1 over 3 plus 2 times 8 plus 1 over 3 times 8 to the power of negative 4 over 3 times 0.02. Ultimate value is 63.82.
Hence, we can conclude that differentiation techniques are essential shorthand tools that allow us to calculate the slope of complex curves without relying on the lengthy and difficult limit definition. Ultimately, these techniques provide consistent step-by-step process such as identifying, differentiation, and combining to solve real-world problems in physics and engineering that turn what would be an impossible manual calculation into a manageable algebraic process. That's a wrap for our presentation.